Now today we're going to put together the three laws that we talked about the last time, Boyle's Law, Charles' Law, Gay-Lussac's Law, and we're going to combine those into one equation for one set of relationships, okay? So that is called the combined gas law, and in this equation you can see that pressure and volume are on the top together. So what that tells you is that if one goes up, the other's going to have to go down to be able to keep the value equal on the other side. Since pressure and temperature are above each other or on top of each other, if one goes up, the other one's going to have to go up in order to keep the volume the same, or in order to keep the relationship the same. Volume and temperature are the same way since they are above each other, one in the numerator, one in the denominator. If one goes up, the other one's also going to have to go up to keep the ratio the same between them, okay? So this is a combined gas law. Now, one other thing that's a little bit different in this module that I haven't expected you to do before is as you're working your way through the module, I want you to keep an index card, a small piece of paper that has any equation that you think you may possibly need for your test at the end of the chapter. I'm not going to put the equations on the test. It will be your responsibility to write down any equations that you think you need. You can put down anything on that card that you want it to have. In the United States, we have 3-inch by 5-inch index cards, which are about that size. So that would be approximately the size that I would expect that you would be using. If you're in a location where they're not exactly that size, that's not a big deal. But this is approximately the size that you want to be using to write down your equations on there. So this obviously would be one equation you're going to need to write down because you're going to be using this one a lot. Another relationship that we touched on the last time when I talked about extrapolation, you can see that the temperature is on the bottom, and you should hopefully know that you can't ever divide anything by 0. And we know that we can have a temperature of 0. We know that that's the temperature where water freezes at is 0 degrees Celsius, and we know temperature can go below 0, but we can't ever put a 0 in the bottom of this because that's an illegal action. It won't work. You can't divide by 0. So what we have to do instead is we have to convert to an absolute temperature scale, which is the Kelvin scale. And so if you can't actually get to 0 Kelvin because that's the temperature which is the same as a negative 273.15 that I showed you on that graph the other day. And again, I know that you've read about this already. So if I have a negative 273.15 and I add that to this, then I will end up with a temperature of 0 Kelvin. That is not actually obtainable. You can't have a temperature of 0 Kelvin. But that's the temperature scale we're going to use so that we always have a non-zero number in the denominator of these fractions up here. All right, let's try to work a sample problem. So the sample problems I gave you in a separate document. Hopefully you've got those printed out and have them in front of you because we have two sample problems for today. So we'll look at the first one. A gas is stored in a 3-liter container at a pressure of 456 torr. If the temperature stays constant, what will the pressure of the gas be if the volume is decreased to 0.75 liters? Okay, so if anytime that you have a change in conditions, which is what we have here, where the pressure is going to change and we know that the volume is going to change, we're going to use this particular relationship because this side are the initial conditions and then this side is the final conditions. So let's look at what we've got here and start plugging this information in. So it says a gas is stored in a 3-liter container. So 3 liters is volume 1. So I'm going to have 3.00 liters at a pressure of 456 torr. So that's my initial pressure, 456 torr. Now, what's nice about the combined gas law is that it doesn't make any difference what units I'm using. As long as they're the same on both sides, they're gonna cancel out, and so it will work. That will not be the case a little bit later on in the chapter, but your pressure and your volume units can be whatever is already in the problem, and that will work just fine. Okay. It says the temperature stays constant. So the temperature is just going to be T, because they didn't actually give me the temperature. And then it says, what will the pressure of the gas be? So I don't know what the new pressure is if the volume is decreased to 0.75 liters. And temperature is constant, so it's the same on both sides. Okay? Well, if it's the same on both sides, it's going to drop out. It's going to cancel out. So I don't have to worry about that at all. And so now I just have a real simple equation to solve. Now, what I want you to do as you're working these problems is I want you to really think about what's going on here. If I'm only relating pressure and temperature, if my volume went down, what's going to happen to my pressure? So I'm squishing things together, but the temperature stays constant, so the molecules are still moving at the same rate they did before. What should happen? Well, it should be that my pressure is going to go up. If the volume goes down, the pressure should go up. And when you do that, that's what you should find. So if you take your calculator, you take 456 times 3 divided by 0.75, you will end up with a pressure of, get the right paper here, 1800 torr. Okay, my marker has decided it doesn't want to work. Okay, so a new pressure of 1800 torr. So obviously what we had calculated or what we had thought in our head was correct, and the pressure has definitely gone up. Okay, now for the second problem, it's not going to be quite so nice because we're going to have everything changing. So I'm going to grab another marker here. Hopefully that will work better. A weather balloon is filled with helium before it is launched. On the ground, the gas has a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. The volume of the balloon is 4.5 cubic meters. As the balloon rises, however, the pressure and temperature change to 0.3 atmospheres and 15 degrees Celsius. What is the new volume of the balloon? Okay, so in this case, everything is changing. So it's going to be a little bit harder to think through as to exactly what's happening here, but we're going to give it a shot anyway. First of all, you will notice that the temperature is not in Kelvin, it is in Celsius. And we said anytime we use this law, we have to have our temperatures in Kelvin. So that's the first thing I'm going to do is I'm going to change these temperatures to Kelvin. So my first temperature is 25 degrees Celsius. So I need to add 273.15 to that, and that will give me a temperature of 298 Kelvin. Remember, when we add, it just depends on, the significant figures depend on where the decimal point is. Okay. Similarly, if I have a temperature of 15 degrees Celsius and I'm going to add 273.15 to that, I will end up with a temperature of 288 Kelvin. Okay, so those are the temperatures I'm going to use. So now we can use the combined gas law to get everything else plugged in there. So it says on the ground, which is where the balloon starts. So that's going to be where the balloon starts was at 25 degrees Celsius or 298 Kelvin. Notice when you write a Kelvin temperature, it does not have a degree sign on it. It's just 298 and then a capital K. The initial atmosphere or initial pressure was 1 atmosphere, and the initial volume was 4.5 cubic meters. Okay, and I can use those as long as the units that I use on the other side are the same. Okay, so once the balloon starts to rise, I end up with a new temperature of 288 Kelvin, which was the 15 degrees Celsius that I already converted up here. And then it says my new pressure is 0.3 atmospheres, and so I want to find out what the volume's going to do. Now, again, this one's a little bit harder to think through, but let's give it a try and see if we can predict what's going to happen here. My temperature is going down, so if my temperature is going down, what should happen to my volume? Well, if the temperature is going down, the volume should be going down as well. Okay? The pressure is going down, So what should happen to the volume if the pressure goes down? Well, if the pressure goes down, the volume should go up. Well, how am I supposed to predict what's going to happen if the temperature tells me it's going to go down and the pressure tells me it's going to go up? Well, sometimes you can't tell and you just got to plug through the math and see what happens. But in this particular case, if I look at how much it's gone down, I went from 298 to 288. That's not a huge amount of change as if you look at the pressure, which went from 1 atmosphere to 0.3 atmospheres. So here my atmosphere is less than a third of what it was before, and in relation, the temperature hasn't gone down a whole lot. So what I would expect to happen is probably that my volume's going to go up and that my balloon's going to get bigger as it rises, okay? So again, if you make a prediction and then something doesn't go quite right, you can go back and say, okay, did I make a math error or did I just predict it wrong, okay? Now, one nice thing about these, what I always like to do is I like to cross multiply with these types of problems. If you have another way you prefer to solve it, that works too. I don't think he mentions cross multiplication, so I'm going to show you how to set that up this way. Remember, you can cross multiply to solve proportion or ratio problems. So if you take 1 atmosphere times 4.5 cubic meters times 288 Kelvin, that will equal 0.3 atmospheres times 298 Kelvin times V sub 2, okay? Then you're going to be able to divide both sides by the 0.3 atmospheres and the 298 Kelvin, and then you should end up with a new volume of 14 cubic meters, okay? And that is to the correct number of significant figures because these guys only had 2, okay? So you can see that our prediction was correct. The volume did go up because the pressure change was much more substantial than the temperature change was here. Okay, so as you're working through these problems, see if you can think through, see if you can figure out what is going to happen as the situation plays out, what should happen with your answer, what should it look like at the end, because that will, first of all, help you to internalize the concepts, and will also kind of help you check yourself with your work.